get a bit of glow from the
Slate there, so if somebody wants it.
Yeah, anybody want?
Or if anybody
Yeah,
wants
we
to
don't know
claim
who
it.
said this. Okay, there you go.
Oh, the remote is right there in front.
Oh, yeah, right.
Okay, I did this morning, so I'm not sure what I put on here.
Because this morning was a long time ago.
The space station's coming over at
Oh,
what
at
time?
9:35.
9:35. 6 people on there. They just launched another 3 people up just a few days ago, and it's linked up, and everybody's happy. So if we get a chance to see the space station go overhead, there's 6 people on there. Let me. The big thing that's going on Mars right now is dust storm. Huge. That's the same thing we're going through. This gives you a feel for what's like on Mars. So, but there, even when I finish this thing, the PowerPoint, I realize that opportunity is really going through a nightmare because it has so. Curiosity is the 1-ton rover we got there in August of 2012. It's nuclear powered. Opportunity just has been, I don't know, how many, what did I say, 15 years in operation. It's got solar panels, so they're pretty worried about the dust storm. That'll cut the energy down for the Opportunity rover. But anyway, they're watching this huge dust storm on Mars right now, and Curiosity, this is a picture from Curiosity at the Go crater. Pretty cool things have been happening with Curiosity on Mars. One, the drill that it has broke down, and they had some real issues with the drill. Came up with a new technique to use the drill. It took them quite a while to fix this drill operation, but this is a robotic arm going into the drill hole, made a new sampling. They're still analyzing this piece of Mars in the Curiosity rover, and we'll hear some new, I think, pretty interesting new data about what they found. But what they had the other day was a pretty cool methane story, about Mars, and we're getting close to some kind of agreement about, did Mars, is it there now? But this is a pretty compelling NASA story as of a few days ago about this methane spike that they're seeing in the data. And this is one of those, I'm a believer that life is on Mars now, aquifers, underground, we're seeing some spikes. One of the best things that's happening with this data is that the Europeans have a trace gas orbiter around Mars right now, and it's actually got some methane sensors on it. So we're going to get a pretty good profile of Mars that I think will maybe help seal the deal about, was there life on Mars? Is there life on Mars? It never happened. It's there now. We've spent billions trying to get the answer. And I think hopefully we'll have some closure.
Can I ask a question on that one?
Yeah.
Is that local, that methane spike, or is that,
That's local where Curiosity was.
okay, so it's right.
Yeah, it's right where it is.
Okay.
Yeah, so I think that's the big thing coming out of the European orbiter. It's a global, it's orbiting, so it's going to have a much different profile of this methane spike. This has been one of those topics that's been going on for years, again, around the landing site. And they're going to decide in the end of the year, I think I know where it's going to go, but there's like 3 landing sites, and they're going to pick one, and from there, let's hope it all works. This mission is so cool, if it works. It has cameras on it. It has microphones on it. For the first time, we'll hear Mars. We'll actually have much more participation in the landing with all these GoPro cameras all over the place on the descent. So, but bad thing, okay, that sounds good. Bad thing is it has to actually land successfully so it can relay what the GoPro cameras took. So if it's a failure, we'll know pretty good. Another Mars thing, I'm kind of a Mars guy. InSight's on its way. I don't know if you remember maybe the last time I talked about InSight getting launched. When was that launch, Barb? May 5th? What? May 5th, okay. It'll land in November 26th, I think, something like that, or something like that. And it's en route now to Mars. This is built by Lockheed Martin. It's going, and things look pretty good. Seems like it's working. It'll look for Mars quakes. It'll be kind of a interesting spacecraft. It has retro rockets. It lands on Mars. It's going to has a seismometer that had a lot of problems that delayed the mission for a couple of years. They fixed that. It's a French instrument, so it's going to be, I'm sure, work fine. I do want to just touch on something that's happening in the background of all the space stuff, and that's private space operations. This is Jeff Bezos. How many people know Jeff Bezos from Amazon? He's the billionaire. He's probably the wealthiest person on the planet. He has developed he's got a whole string of rockets. If this one has been tested for suborbital flight, eventually, maybe in the next year or so, he'll be flying passengers on a suborbital track. It just had another successful mission just not too long ago. Another one that's coming up is Richard Branson with the Spaceship Two. Again, I don't know how many people have $150,000 in the bank. You can get a seat on this thing. It's working pretty well. This is a suborbital space plane that Branson is pushing, and
Hey Leonard, I think it's 250,000. No,
so 150,000.
Is that how much you paid to send him out?
Can't go. Can't go.
Oh, I'm sorry.
Is it 250?
I think so.
No, I
It
think
might be even 300.
If you have a coupon.
Anyway,
Yeah, there may be a coupon.
maybe it's not that cheap. You do get to keep the helmet. You get the suit.
They're training.
Because you probably,
But it's suborbital. You go near Earth space and you go up out of the atmosphere and you come back down. It's a long process, but it's and Richard Branson, I just learned today, is undergoing some centrifuge tests because he wants to take his kids. So I think he's going to be on the first flight of this thing when it's operational. Anyway,
Didn't they just have a
they've
second
they've
thing?
had some real successful flights of this vehicle now, and it's getting close. This all happened in New Mexico when they have, the Spaceport of America is the spaceport of choice for this operations of this vehicle. So we'll see how this evolves. I think the other thing I'm watching a lot is China. They just launched a relay satellite that will wind up in an L point around the moon as a relay station to communicate with the far side, because they're going to launch it probably by December. End of the year, they will launch the first lander to the far side of the moon. So they first launched this relay satellite that will actually communicate with this lander, and watch that space. The biggest thing that happened in China in the last few weeks was they announced and put out through the United Nations kind of a guidebook on making open their space station to the world. They're trying to get people to think about experiments. Other countries can participate. It's a diplomatic statement, but it's also at a time they want to put this station together by 2022. That's their sort of the time frame. It's a little ahead, if they get it up there and it all comes together, it's a little bit ahead of the reentry of this thing, the International Space Station. And China, we're in some kind of diplomatic space race that I think is really formidable. And we'll see what America is going to do with this International Space Station. We're talking about trying to re-enter this thing in 2024, 26. How long will this thing last? Should we have it up there to, politicians are talking about 2030. How safe will it be? So I think there's a little bit of a diplomatic card that both China and the United States are playing on use of International Space Station.
Do we have a choice of whenever he enters? Can we?
Yeah, well,
Lose that thruster?
somebody will, yeah, but don't get me going. To try to bring that crazy thing down, it's insane.
Yeah. It's
I don't see how they're gonna do it. I just don't, I don't get it. You know, I've talked to people, that thing is so layered with, material and wiring and everything else. You know how much money that's gonna cost to even break apart? You know, and then the last time I looked at this, they were actually working with the Russians trying to get progress, their spacecraft to actually link up and try to knock it down and put it in a Pacific Ocean kind of thing, where you re-enter the whole thing. And, we're talking $150, $200 billion worth of space station.
So why intentionally bring it down? Why not leave it up until it fails and then bring it down?
There you go.
Okay, so we're in agreement.
Yeah. I don't know. Bust it up, do something else with the facility. Now, it could be that, the new NASA administrator is actually talking to a lot of private groups that taking this thing over and using it. But we're talking, this is billions of dollars a year to run. And this is probably the quagmire that NASA's in now, because unless the NASA budget goes up in some significant way, putting money into this thing is negating other missions, other outer planets, pick anything. Budgets are budgets. So, so we have a kind of a quandary on this thing, and on the other hand, this thing is turning out to be a pretty good research lab. I mean, if you really look into what's going on in that thing, it's significant. I mean, it's significant. We're learning a lot about space facilities and, life science and life support systems and everything else. I'm kind of a big believer for a guy that wrote, "This is a white elephant." So I'm changing my tune there, but now what do we have? What is it? How are we gonna get rid of it? Or we build on it or do something else with it? And that's a great question. Congress has had multiple hearings in the last 3 months on this, and you can pick any.
Could you tell me, I don't know anything,
Yeah.
so I just wanna know how long is it, how long is that from end to end?
Giant football field size thing. Yeah. It's taken years to, put all that glue, all that stuff together. Early on, when you gotta fill in something there.
Well, question,
Yeah.
has it started to get glitchy or maybe some impact adjustment to get something to work right?
No, it has like your home. We got stuff we haven't fixed yet. Summer. The deck need painting.
Are there human lives at stake if some break?
I think you can make a case that lives are at stake in human spaceflight when given orbital debris, But this thing has taken some hits already with small impactors. And God love them. There have been occasions when they've asked the astronauts to sit in the Soyuz as a rescue vehicle because they weren't sure about an orbital debris impact. That's how severe some of these collision potentials are, that they've actually asked the astronauts to sit in the Soyuz in case something hits. Can you imagine being a couple hundred miles above the Earth and going sitting in the thing waiting for a loud bang?
There's a movie about that.
Anyway, no, it's a great story. We'll see where this is really going to evolve, but it's a lot of money. Keep an eye on Japan with a new asteroid mission that they're just pulling up to their target. What did I say? I just wrote it down. Okay. June 27th. This is by the JAXA group, the Japanese Space Agency. Amazing vehicle. It's almost at its target. It's going to actually bomb an asteroid with an impactor, go down, sample the crater that it makes, drop off a bunch of robots, pick up some samples, and then come back to Earth. It's pretty cool. Yeah, it's a great mission. I wish them the best. They've had, so far so good, they're closing in on the target. Like I said,
What's the name of that?
Hayabusa 2. Yeah, pretty cool. Then we had the big wake-up call for Alan Stern's benefit here. He can sleep tonight. The New Horizons spacecraft got woken up and getting ready for its first of the year, end of the year. What are we talking about?
December,
New
New
Year's
Year's
Eve.
Eve.
Rendezvous with a Kuiper Belt object, so it's looks like it's up and alive, right? We're in good shape.
Ultima Thule is its name.
What's, how do you? Yeah, I wrote it down.
Ultima Thule.
Okay.
Thule.
Okay. Cool.
Thule.
And that was a citizen selection name?
Yeah,
Yeah. Okay.
Beyond the known world.
Yeah, it's a great
And
mission.
that was the spacecraft that went to.
That's it.
Pluto.
A lot of stuff going on. Really a fun time to follow this from a journalistic standpoint, but I didn't go through Juno, as our speaker is. Fran is well, I wore this shirt on purpose. This is my Mars shirt. Every time I'm in her office, we yell.
Don't worry, I got my own.
Yeah, I know.
Well, we
So-
all need Juno shoots.
I don't have a Juno shirt. I
We
wear
don't
it.
have a Juno shoot. or
But-
Jupiter.
From the University of Colorado Boulder. I've known her for quite a while now. I don't know when I first met up with her, and we've been yelling ever since. But she's leader of the plasma investigations on the Juno mission at Jupiter, and also key leader in the New Horizon mission to Pluto. But it's great that we could get her here tonight, and I'll try to change my shirt in the car. Thank you for coming. Fran Bago.
What that piddly little piece of Mars. And by the way, the press release, if you read the press release, says that what they found is that that methane is totally consistent with it being entirely inorganic and it has nothing to do with the non-existence of life on Mars.
So this is why we yell.
This is why
They wasted
More to
all
come.
these billions of
More to come.
dollars to send things to Mars again to rediscover. Okay.
Did they find water on Mars yet?
So I'm going to talk about Juno and the Juno mission to Jupiter. It's been in orbit for nearly 2 years now. And as you know, Jupiter's big. And the important point here is not that it's 10 times the size of the Earth, but it's actually 318 times the mass of the Earth, and that's going to be important when we look at what it's made of and its role in the solar system and so on and so forth. Okay, so when we look at Jupiter from the Earth or from a spacecraft that flies by the equator, all previous observations have been such as this Cassini one in the equator looking at the equatorial belts and zones. And what you see are these east and west winds, you see the great red spark going around, you see a bunch of other winds and so on and so forth, but we haven't seen a pulse from the ground or from a spacecraft flying by. We haven't flown over the poles until we had Juno. So that's one of the important targets. Let me just talk about a little bit about what we're looking at. When we're looking at Jupiter, we see white clouds. Those outermost layers are ammonia clouds right at the top. And the atmospheric pressure is sort of similar to the pressure in this room at the top of those cloud disks. And, but we also see coloured clouds. And those are probably, we think, photochemical smog, like the brown cloud that we have in Denver, where sunlight has reacted with chemicals, very small amounts of them, that colour some of the clouds. And you'll see that later when we look at the pictures. So the colour is probably an indication that those clouds have been around a while and have pulled together some of that photochemical smog that's accumulated over time, white being fresher clouds. Now we think that underneath this ammonia cloud, there's an ammonia hydrosulfide cloud, which may or may not be orangey coloured, and then below that, water. And that was the idea of what we think, based on the chemistry of what we understand about our solar system, what we would expect those cloud layers to be like. Now we sent a probe into Jupiter's atmosphere. The Galileo probe went in, and we were expecting to see these 3 layers of clouds. This is what we saw. Virtually no clouds at all we went through. So the big question then was, where is the water, which we think there should be a lot of, not to mention the other clouds. So what actually happens, it turns out, we didn't drive the probe in, we just sort of dropped it off and it landed where it landed. And what happens is it went in between those east and west belts and zones into what we think is a Chinook area, a dry area, with very dry winds descending. And so it could be purely meteorological. And at the same time, we looked from Hawaii and saw a hot spot. It's an indicator that this was a hot descending region here. And so maybe we just went into the wrong place. And this is important because we really want to know what it's like inside Jupiter. The reason we think it's important is that the gas giants, the current idea for formation of the solar system is that you have a star at the centre of our sun, cools off, and you've got this big cloud of material around the sun, and that the rocks and metals condense out to make the terrestrial planets like Earth. But beyond the frost line, there was a lot of snowballs accumulated where you would have cold enough to have ice forming. Those snowballs would get big enough, eventually, if you end up being 20 Earth masses.
You're talking about water ice, please?
Water ice, in this case water ice, but there would be mixed in with that water ice, ammonia and methane. Water, ammonia, methane, I talk about wham, right, if you like. But mostly water ice, with other stuff mixed in that would condense. But once it gets to be 20 Earth masses or so, which is what we think the centre of Jupiter is, pulls in, the gravity is enough to pull in all the hydrogen. So you end up with this big gas giant planet that has at its core, we think, ice, right? Mostly water ice, but also other stuff. And so we think that these gas giant planets have this central core that is ice, or was originally ice. Now the other thing is that when you look at the cosmic abundance of elements, the third most abundant element after hydrogen and helium is oxygen. You mix oxygen with the most abundant element, hydrogen, you get water. So if we can't see water on the largest planet in our solar system, then we're kind of missing something pretty big here. Just the total inventory of the material, but also our ideas of formation of the solar system. So one of the major goals was to go with Juno to go look at, to see where the water is, which is important for understanding the amount of oxygen in our solar system, understanding how the gas planets formed, and since we're going to fly over the poles, we can get to look at the aurora and do some magnetospheric physics, which is what I like to do. Okay, so I'll tell you a bit about that. So this spacecraft is really cool. It would not fit in this room. It's too big. Look at the human here, right? So this bit, this spacecraft bit would fit. It's, you know, like this big, right? But these panels are really long. They're 60, so it's a 60-foot diameter spacecraft with these 3 solar panels, and generating about 500 watts of power, and it's spinning every 30 seconds. That's, you know, that keeps it stabilized, but it also allows us to make our measurements of the planet as we fly over. Now the instruments we've got on here, on the end of this solar panel, we have the magnetometer with some star trackers that will help us get the orientation right. And we put it on the end of the solar panel to be away from any electrical currents, any sorts of noise that is in the spacecraft. We have a couple of energetic particle instruments, charged particle instruments, low and high energies. We have a wave instruments that measures radio and plasma waves. We have an infrared spectrometer that came from Italy. We have a UV spectrometer. We have a microwave instrument that measures, we'll show you about that. The microwave is important for looking to see if we can see the absorption of the microwaves that are coming from the hot, deep interior, out through the clouds, out through the water. And you all know that microwaves are absorbed by water. So we look for the absorption of the microwaves to get the signature of the water and the ammonia. And we use gravity science, I'll show you how that works, to measure the mass and to see what it's like inside. Now, of course, tacked on up here is a little camera. This is a camera that was added on later. All NASA spacecraft have to have cameras on them, right, take pictures. We added it on, and it's got mostly images that have been processed by the citizen scientists, and I'll show you why this has been such a major success of this mission. Okay, so the whole point about getting up close is we want to measure the amount of material that's inside. So you've got to get up close to measure that, either gravity field, magnetic field, and the microwaves. You've got to get up close. The problem is with Jupiter is that around it there is this donut of very energetic charged particles. So 10 MeV electrons that are trapped in the magnetic field all the way around, that is lethal for electronics. You just don't want to put your computer through this sort of radiation. And so we need to duck under the radiation belts, over the clouds, in an orbit that's like this. Now the problem is that because Jupiter rotates every 10 hours, and it's 318 times the mass of the Earth, it's got a lot of mass. It's a liquid. Think of a rotating liquid. The equator is fatter than the pole, so it's squished. Right? It's got a fat belly band, and what that does to the orbit, the gravity of that distribution of mass, moves the orbit automatically down. So we go from orbit 1, 16 to 32 like this, and so inevitably around orbit something, 30-something, we will start to go into the radiation belts. And there's nothing we can do about it. That's just force of nature. Okay, so that's the plan. But also note that because we're getting in very close to Jupiter, we will be moving at about 60 kilometers a second, which is about, I don't know, 60,000 miles an hour, something like that. I can't do the...
Really damn fast.
Sorry?
Really damn fast.
Really damn fast, yes. Yeah. Actually, it's equivalent to going around the Earth 5 times in 2 hours, right? Right, so that gives you a sense of the speed at which we're moving as we go over. Okay, and the idea is to about 30 orbits, we'll map it out. That's what the current announcement of the continuation of the mission is, to get these 32 orbits and map out the magnetic field and the gravity and so on.
What's the length of an orbit?
The orbits are 53-day orbits, and so they come in really close to the planet and then they go out and they spend the rest of those 53 days all the way out here and come back in. And the full length, the semi-major axis of that orbit is 113 Jovian radii. 113 times the radius of Jupiter. And so the size of the Sun is 10 times the size of Jupiter. So that's 10 times the size of the Sun, if you like, is the scale of the orbit, if that gives you some sense of the scale.
It's orbiting now, right?
It is orbiting right now.
Which number is it on?
It's just done 13
Okay.
last week. Yeah, good. Yeah. So we're kind of a third of the way through. A little more than a third of the way through. Yeah. So what the idea is to see, this is a cartoon picture you had in all your textbooks of this layers of the interior of the planet. But if you talk to some expert physicists, they will say, at the pressures deep inside Jupiter, we actually expect the hydrogen to dissolve these molecules, these ices, the ammonia and the water, and turn them into just elements. So you just have oxygen and carbon and iron and silicon, all these things that will dissolve in the hydrogen and get mixed up. And so the idea is, by measuring the gravity, we can test, is it like this, separate layers, or is it much more mixed out with the heavy elements, more spread out with the hydrogen? And that's the idea.
So on
Yeah.
this chart, I'm sorry, I don't know if
Okay.
you did that well.
Okay, let me go back.
You said it's called a gas giant,
Yes,
and you're saying it's kind of liquidy. What parts
Okay.
of that would be liquid, gas,
Okay.
solid? What
Right,
are we looking
right,
at?
right, good point. Okay, certainly it is true that if you went in with a spacecraft, you would not land on a surface. There is no rock surface here, right? What happens is you go in, the pressure increases, and as the pressure increases, once you get down to about 80% of the radius, you get to a point where the pressure is about 2.5 million times the pressure in this room. Okay? 2.5 megabars.
So not very comfortable.
That, not very comfortable. And at those pressures, hydrogen turns from a gas of a proton and electron working together into a plasma. That is, the protons and the electrons move separately. And it becomes electrically conducting, right? If you can move the positive and the negative charges relative to each other, you can have currents, electrical currents conducted in this liquid. It becomes a liquid metallic hydrogen. And we've made this actually in the lab. You can make it at Lawrence Livermore. Gee, isn't that where they study hydrogen bombs and hydrogen and high pressure? I'm sure it's, I don't know any of this officially, but I hear, actually that's not true, it is published in the literature, the scientific literature. It has been published that at these pressures and temperatures, you will end up getting liquid metallic hydrogen. And it's that liquid metallic hydrogen that probably, if you were to pick it up, which you can't, obviously, we've never been at those sort of pressures, it would be like mercury, liquid mercury flowing around. So that's where we think the dynamo is. That's where we think the magnetic dynamo is at Jupiter. So just like the liquid iron that we have in the Earth's interior, where we have our magnetic dynamo, inside Jupiter and the other, and Jupiter and Saturn, not Uranus and Neptune, the pressures aren't high enough. At Jupiter and Saturn, they have this region of liquid metallic hydrogen deep inside. And because it's a rather exotic material, and it's at pressures and temperatures that you can't actually make in the lab once you get really deeper down inside, we have to rely on theoretical models, and those theoretical models are the ones that are telling us that perhaps these things we call ices and metals and rocks become separated into elements that are dissolved in the liquid metallic hydrogen.
Wow.
Does that answer your question?
Yeah,
That helps?
so
Yeah.
your new model is kind of, it's a liquidy all the
Yeah.
way throughout.
Yeah.
And so when you said it had a 10-hour rotational time, is that the exterior of it, halfway through the center?
Excellent question. This is why I love coming to talk to astronomy because you guys ask the best questions. Right. Okay, so yes, good point. Actually, what we measure is the magnetic field. The magnetic field of Jupiter is tilted by 10 degrees, like ours is tilted, like the magnetic axis is off a little bit from the spin axis. And so every 10 hours, we see the magnetic field wobbling around. And we've been doing this since before the beginning of the space age with the radio emission. So Jupiter emits radio, right, because of the particles trapped in the magnetic field. A lot of, huge part of those observations have been made by amateur astronomers, a lot of radio astronomers who've been putting up their antennas in the backyard and observing Jupiter emitting radio. We tried to do it in Boulder, even though they had some of the big papers were written from the antennas in Boulder, in the university. We tried to do it this summer with some students with a radio. You can't, there's too much noise. You just can't hear it. It's really frustrating. But there are a lot of people who have a radio equipment in their yard and can listen to radio emission from Jupiter. And it's that 10-hour oscillations of the radio emission that tells us the spin rate of the whole planet, the big planet. But of course the clouds, the red spot and the clouds move relative to that spin rate. And so that's, again, what a lot of people have been observing with their own telescopes, watching the clouds and watching the spots go around relative to that rotation rate. Excellent. Okay, I've got to get on. Okay, so what we do now is we use Doppler shift. The spacecraft is moving around Jupiter, sending radio signals back to the Earth. And if there's a perturbation in the motion of that spacecraft due to distribution of mass inside, so you get a wiggle in that trajectory, then the Doppler shift of the signal will be perturbed, will be changed. And so from the Deep Space Network, when we listen to the radio signal from satellite, we can measure small motions of the spacecraft that are caused by the distribution of mass deep inside the planet. Now, this is a similar technique we've used throughout the solar system to measure the gravity of the planet by measuring this Doppler shift of the radio signal of a spacecraft going by. So this is a known technique. It's very precise. Okay, so we measure the magnetic field, we fly over, and we're trying to work out where the dynamo is produced. So the dynamo, like I said, is produced in this liquid metallic hydrogen phase, and the spin, you need a bit of spin to have a dynamo, and you need to have heat conduction to turn over the interior. These are the main ingredients of a dynamo, and you need to, the heat inside is enough to drive this dynamo inside Jupiter. And a large volume, because the mass is so large, is this liquid metallic hydrogen. You have a very strong magnetic field. We will also want to look at the higher up, where the water is, the one drives the winds, and that's where we use the microwave. So if you look in infrared, and this is an infrared image taken by the Infrared Telescope on Hawaii, you can see that there's dark areas which are black. Those are the high white clouds. Observed in the visible light, they look white, but in the infrared they look dark because they're cold. They reflect the sunlight rather than letting the heat through from the deep interior. Between the cloud decks, you see these bright heat escaping from between the clouds and coming out there. Now, the infrared only sands the top layer, the sort of the ammonia cloud at the top. It doesn't measure down. You need to use microwaves, and we have 6 different wavelengths that go down to about 300 or 400 kilometers down. So we go a long way down through the atmosphere with the microwaves and measure the composition. And this is where we want to be able to measure the ammonia and the water clouds deeper down using that technique. And like I said, since we happen to be going over the poles, we can measure the magnetic field of Jupiter, but we can also measure the magnetosphere. This is a very vast region, so you could take all of the Earth's magnetosphere and put it into the planet Jupiter. So the Earth's magnetic field spreads out for about 10 Earth radii in the direction towards the Sun. That's sort of the bubble, magnetic bubble that protects our atmosphere and life on Earth. But at Jupiter, because the field is so strong, it extends for 100 Jovian radii out here, and so that's equivalent to 10 times the size of the Sun. So the Sun, would be sort of this size on this scale, and so it's vast. Not only that, but away from the Sun, we know, Voyager 2 told us, that this magnetosphere extends all the way to the orbit of Saturn. Because when we arrived with Voyager 2 at Saturn, we measured those perturbations associated with the tail of the magnetosphere. And most of the trouble comes from this moon Io, the innermost of the 4 Galilean moons, that spits out about a ton a second of sulfur and oxygen, volcanic gases. They get broken up, ionized, and trapped in the magnetic field. Okay, so Io, innermost of the 4 Galilean moons, and we detected the volcanoes, totally covered in volcanoes, not a single impact crater. It's a very old surface, turns over 40 times in the age of the solar system. And the white stuff is sulfur dioxide gas that's condensed on the surface, and the dark blobs are volcanic rocks, like volcanic rocks on Earth. And when New Horizons flew by, persuaded Pluto, got a gravity assist, measured Tvashtar, this big plume erupting sulfur dioxide and dust into the atmosphere. And now this is a picture from Duran, the infrared instrument on Juno, that shows all these hotspots all over these volcanic eruptions. So I hate to say this to the poor people in Hawaii, but eat your heart out. This is way more reactive. Okay, so this nanosecond of stuff becomes ionized, trapped in this magnetic field, produces another donut further out of ionized gases that emit about a terawatt of light in a UV, and then million amp currents flow between the moon and the planet, generating aurora, and I'll show you some pictures of the aurora associated with Io. Okay, so here we are. This is the Hubble Space Telescope picture. Io with aurora, a footprint associated with Europa and Ganymede, and then this is the main auroral oval, which we've been observing. And let me think, I have a movie here. This is a Hubble movie as Juno was approaching. You can see the Io extended tail. Europa comes and goes. This is Ganymede. Remember, Ganymede is a very special moon. Anybody remember what's so special about Ganymede as a moon? It's the largest, yeah. But not only that, it's the only moon that has its own magnetic field. It has a dynamo inside. Probably an iron dynamo, like the Earth's iron dynamo. Really weird. Okay, so magnetosphere with a magnetosphere, so you're Ganymede. Okay, so what we're going to do with Juno, what we're doing, we continue to do, is to fly over the aurora, measure the aurora with the UV and the infrared instruments. We're going to measure the radio waves, the magnetic field perturbations, measure the charged particles that come in and bombard the atmosphere and excite the aurora. So try and work out what's going on with the aurora and understand the physics. Is it similar to the Earth or is it very different? Okay, so we need to build this spacecraft. It was built down at Lockheed Martin, South Denver, and these are the two plates with various things that are strapped on, and you're going to see there's a vault where we protect the electronics by putting it in this vault with aluminum around it to keep it protected. I was allowed to go visit and have a look. I'm not an experimentalist, so I sort of kept my hands very tightly on my sides. But it was beautiful to see this thing that took, I think, about 18 months to put together. Did you work at Lockheed?
I did, but not on this.
But not on this one. Yeah, I think it took about 18 months. I mean, putting these things are complicated. Putting them together takes a lot of work. I'm really impressed with what they did. Here are the solar panels that come out, and you can see the scale of these things. They fold down after launch. They're deployed. So then what you do is, of course, you strap it onto the top of a rocket. You put the stickers on. You take a selfie, and then you launch it, right? And, everything went perfect.
It's amazing how much you just simplified all that.
I know.
What do you think, Tommy?
Stickers, gotta keep that.
I foresee you using this in a presentation of yours next week. So.
This is, I agree. I'm underestimating what's involved, but I want to get to Jupiter. So we launched in August of 2011. Went out and did a maneuver and came back. Earth gravity assist. So we didn't have enough oomph to get out to Jupiter, climb out of the sun's gravity, but we got a kick at Earth, came back out again, and arrived at, it says 7/5, 2016, but of course, it was the 4th of July when we got here. Okay, so, I want to check. Okay, this is full, yeah. So, we came on approach. We approached from dawn, so the sun's over there, here's Jupiter, we come in, we're at the terminator, come in on approach, do a orbit insertion, and then go into these long orbits. And this was a unique perspective. If we could maybe turn the last of the lights out, it really is worth seeing this. This is the first time ever that we have had a movie, we've made a movie looking at Jupiter and the Galilean moons, of course, making the same observations that Galileo made with his Galileo telescope. But we have this little camera, which is this size. It's about the size of an SLR camera. And this is real images. It is not a simulation. Okay, you're seeing photons that left the sun 40 minutes ago, bounced off Jupiter and the moons, and came into the eyeballs of the JunoCam instrument, the camera. And you can see, we observed over, of course, Eo's orbital period is 42 hours, Europa's is 84, and Ganymede's is 168, 222, and then Callisto's is largest, not resonant orbit. But you can see the light, the sunlight blinks out when they go around the back into eclipse. Let me see this. Go on, Eo, do it. You can do it. There we are. Blink out, blink back in. And they're going around. Come on, Callisto. Come on, Callisto. Well, this is amazing. This is the first time we've ever made this movie, right? And it's really is important. And you will know why this was so important. That Galileo looked at these and made all sorts of bold conclusions based on this ideas. So really nice to capture this. Okay, so
I was hoping it's going to keep going.
well, actually, it did end then. You think it went longer?
No, I was just wondering.
Oh,
did
you
I keep
thought
filming
that we
all
were
the
going to
episodes?
zoom? No, we
Okay.
didn't zoom all the way in.
Okay.
No, we didn't. Actually, we turned everything off about here because we were nervous about getting close to Jupiter and getting close to the radiation belts. We turned off all the science instruments and we got ready for orbit insertion. Turn it up. If you can turn it up. Can you turn it up?
Yeah.
Okay, can we
Go back.
can we go back? Because this is kind of cool. Crank up the volume. There we go.
The scariest thing to me about Juno are the unknowns. So much about the environment that we'll have to withstand is unknown. Nothing's really certain about what's going to happen.
It's a monster. It's unforgiving. It's relentless. It's spinning around so fast, its gravity is like a giant slingshot, slinging rocks, dust, electrons, whole comets. Anything that gets close to it becomes its weapon. Just so happens, deep inside this body are the secrets we're after. Secrets about our early solar system. It's the biggest and baddest planet in the solar system, and it's got the biggest and baddest radiation, the biggest and baddest magnetic field.
The background radiation that we're exposed to on Earth is about a third of a record. What we expect to see at Jupiter is about 20 million of a record. No spacecraft has ever flown this close to Jupiter, flown this deep into the radiation belts.
So the real trick is, we go in close, get the data, and get out. And the first time we go in, that's the most dangerous. We call it Jupiter orbit insertion.
Nothing's really certain about what's going to happen.
Okay. Well, you can tell that JPL is near Hollywood, right? So we survived. The people there, the woman at the beginning, her job is to take the measurements of the radiation belts and interpret them. So she knows her way about radiation. And the guy saying it was a monster and it's really scary, he's head of the mission. And the other people are all the, chief mission manager and so on and so forth. So this was done by the in-crowd making jokes. So, but we did survive. We were a little bit nervous, I admit. All went well. Okay, so we did this orbit insertion, and we went on this 53-day orbit, and we started to gather data. And we measured the magnetic field. Like I said, it's tilted the way the Earth's is. It's actually the opposite direction, but we measured the magnetic field a bunch of times. And what we're seeing is that there are perturbations between magnetic field is more complicated than originally previous measurements. That's not unusual. And in fact, the north is a lot stronger than the south. There's a magnetic anomaly, just like the South Atlantic anomaly for the Earth, and so on. So this is an indication that we're seeing a more structured magnetic field, and which is what we expect if we're going to be able to measure the dynamo. And if we can, this was just from 8 orbits. If we get 32, we'll have a lot higher resolution and map out in more detail the magnetic field of the planet. So this is a sort of cartoon of what we know right now, and it's not just a simple bar magnet. There are these anomalies of higher and weaker field strength region. We don't know why it's stronger in the north than the south, but we're now beginning to look at this and try and work out what's going on. Okay, for the interior, what we have found is, indeed, the mass is more spread out. It's the heavy elements are mixed, and it's not a sharp boundary, which we sort of suspected. So the theorists are somewhat right, and the mass is more mixed in, and we're beginning to see this more material sort of mixed in different areas. We also were looking at the ammonia. We're trying to work out where the water is and what's going on with the water. But what we're finding is that the ammonia tends to indicate there's convection patterns. And here is a sort of sense of the variation in the amount of ammonia. We're only looking around the equator region, but there seems to be enhanced ammonia near the equator and weaker higher up. And so actually, before we can get the water, we actually have to sort out the ammonia before we can understand what's going on. But we're measuring really quite deep, down to about 400 kilometers, and so we're working out what it's like inside. We're using the infrared images. This is infrared images showing all the eddies and so on, a lot more structure in the atmosphere than we can see from Earth. And then we're getting these images. And let me tell you a little bit about the images. And I sort of facetiously make jokes about the camera people on these missions, like Cassini, because they tend to dominate where we're going to point the spacecraft, and this really affects how other people's measurements are made. So people like me who measure charged particles and magnetic fields, you know, we have to go along with the cameras because the cameras always rule things. But on this instrument, on this spacecraft, we just told the camera guys, you know, you'll get to get your pictures. Our data are more important than yours. Right, it's a very sort of macho classic thing to do. But what's really exciting about this is, it is a citizen science experiment. The data are put up within hours of the flyby. All of the data taken, the images that are taken on a flyby, they're made available to everybody. Everybody can download them, play with them, post their results back up again. And so if you go to this website, there's all sorts of interesting stuff. You can get involved in discussions. You used to be able to vote. We've sort of closed down the voting because there isn't a lot of choice of the way the orbit's changing. But you can look at you can go look at what's up there. So the true colour of the clouds are really pretty pale. The Voyager pictures were somewhat exaggerated. We've now got a better sense of what the true colours are. And Bjorn Johnson is one of the amateur astronomers, citizen scientists. I really want to give the respect to these people who've done a fantastic amount of work. They put them up, process them, then other people take them, and they just put it into Photoshop or their favorite image processing program, and they crank up the color contrast, right? And now you can see all this stuff, right? Really cool. And what we're seeing are these eddies. We're seeing all sorts of structure. we can do artwork, people that do cool stuff, why not? All sorts of stuff. This is a fairly recent one. Again, you know, why not? Why not? Why do the arrogant scientists have to have control over all this stuff? So it's really fantastic what people are doing. This is a first view over the poles. We flew over the poles, and for the first time we got to see. It tends to be bluish, radially scattering, just like the daytime skies that we have here, instead of the photochemical smog that's causing the reddish around the equator. Now, because we're spinning, we only go click, 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 click. Next one, click, 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 click. Right? And you don't get a lot of images per orbit. You start off far away, you get the full planet, and then you get in close, you only get a strip because it's a spinning spacecraft. So, but people can put this together in clever ways. This is a multiple images put together to give you a sense of the northern hemisphere of all these vortices around the North Pole. We look in the infrared, and what you see is really kind of cool. The North Pole, you have 1, 2, 3, 4, 5, 6, 7, 8 of these vortices. In the South Pole, you have 5. So North and South are a little different, but they're persistent over the, now we've been looking for these 13 orbits. These jostle and move around a bit every 53 days, but basically the main structure is the same with the North and South being different like this. This ended up being on the front page of Nature, and but what's interesting is you compare it with Cassini at Saturn. So at Saturn, you actually have a polar vortex that's a hexagon. Like, we've known about this hexagon since Voyager. And then deep inside, around the pole, you have this vortex. So a rather different atmospheric structure than you have at Jupiter. And maybe this is related to the fact that Saturn is a third of the mass of Jupiter. So it's not, this means that the clouds are much deeper, and maybe there's a difference in the structure of the dynamics inside. So this is supposed to be a movie. Is the movie?
It's real time.
Oh. Is it moving? It takes a while to get going. No, it's not going. Can we get it to make it go?
Try clicking on the image.
There.
Yeah. Let's just try that.
You're on it.
Is it moving? There we go.
There you go.
There we go.
Yeah, so this sort of gives you a sense of these northern hemisphere, the 8 vortices around the middle one, and this is the JPL guys having fun making 3D. But you can get a sense of the the heat coming from the deep interior, and then these higher clouds being darker and on top. Yeah. Anyway, kind of cool, very different from what we've got at Earth and at Saturn. So this is sort of sending the atmospheric scientists back to computers to generate models of what the heck's going on at these north and south poles. When we look at the visible top left, you see these vortices. You can see them better with the infrared. And then when we look at different layers, much deeper, down to 9 times the Earth's atmosphere, this is 9 atmospheres down, you can still see in the microwave some structure there. So this is all new material that's just coming out, and we're trying to put this together, try and work out what's going on in terms of the dynamics in the northern hemisphere. Now, because we're moving so fast, it's really hard to do movies, but there are little time lapses that give us some sense of the rotation, and this is actually confirming that this is cyclonic in nature, so the atmospheric scientists can go away and say, okay, I've got to make clouds that rotate this way, northern hemisphere, Okay. Some very good work that's been done by John Rogers. He's an amateur astronomer from England who's been looking at the weather on Jupiter for several decades from England. I don't know how he does it from England because, you can't see anything from England. But there are a bunch of amateur astronomers who've been making really good images, and he's retired from being a medical doctor to devote his time to analysing Juno data on the side, and is putting together these sort of weather maps and mapping out where various features are and how they're moving with time. He made this beautiful polar hazes pulling together. You can see the haze around the poles, and then these belts and zones stretching around. So these are the sort of things that people are doing. They're looking at the clouds, cranking up the contrast, showing that some of these eddies have very white centres with dark around them, and the other places we've got dark centres with white around them. Don't know why, but lots of interesting stuff to look at. What is this telling us about the age of these things? Sometimes you see clouds that have little white things. These seem to be what we call pop-up clouds, a bit like the summer storms that we get here in Colorado, where you have clouds coming up, making high altitude, these clouds popping up above. People have been cranking these images to play around with the colours to try and get a sense of the structures. This is exaggerated, of course, but it really tells you that there's a lot of dynamic structure here in these clouds. I like the owly eyes on this one. This is one of my favourite pictures. It's kind of cool. Yeah. So these are just the images that are coming out. I'll only show you a bit about the red spot. This was the Voyager picture. Again, it's an exaggerated colour, and it was about twice the size of the Earth. And this was a movie taken over many days. It takes about 6 days to rotate all the way around, and this is what it looked like at the time of Voyager. Now when we come back and look with Juno, and on the left is the more realistic, the right is where they've cranked up the colours, but you get a sense that this is much rounder, a little less oval. In fact, it's also got a lot smaller. People have been observing the shrinking of the cloud for some time, the Great Red Spot, and it's now about 1.5 times the size of the Earth, not 2 times the size of the Earth. This is again an amateur picture posted up. So now you can see it's rounder, the middle is still very dark, so there's a lot of this photochemical material that's accumulated, and the idea is that it's extended above and below the surrounding regions. Remember that this Great Red Spot has been observed for about 400 years. This is a really long-lived storm. Why the one in the south, not one in the north, who knows? But you can see it sort of seems to be a little rounder than the time of Voyager 40 years ago, and has these very bright white clouds around it. There's some interesting features here. You zoom in, you can see there's some turbulence. And the big question is what's going to happen in the next 50 years. Is it going to completely shrink, disappear? Is it going to break up? Is it just going to grow back big again? We don't know. And this is again where a lot of dedicated amateur astronomers have been helping us understand what's going on with the weather on Jupiter. I just threw in a couple. This was from last week, flyby, the 13th flyby, some really cool structures here. There's another one which was really nice. I like the lighting on this one. It really gives you a sense of the sunlight coming in and the darker poles. So this is, again, from Sean Duran, has done a lot of some of the best pictures. So, yeah. I mean, not bad for public outreach gallery. Not bad. I take off my hat to these guys. They've done a fantastic job. Okay, so I want to just finish up with a little bit more of the other results we've been getting. This is an animation that JPL's put together, giving you a sense of the depth now. We're getting a sense that these belts and zones, these wind systems around the equator that are moving at about 100 miles an hour sort of speed, 100, 200 miles an hour, east and west belts and zones. They extend quite deep, but to the north, it seems like it's much weaker weather systems deeper down inside. So we're trying to work out the weather, the deep weather system, and the interior dynamics of this big gas giant planet. Let me just tell you a little bit about the aurora. This is flying over giving you a sense of how we get this glimpse of the aurora on a quick flyby, and then try and compare it with the local measurements. And before you get dizzy, I'll move on to the next one. Okay. The North and South Pole, we've known for a long time that the North Pole has been a different shape to the South Pole, and now that we've made the measurements of the magnetic anomaly, it's totally consistent with the fact that we have an anomalous magnetic field in the north. In the south, you can see the EO footprint here, and so on. We look at the infrared. You see a lot more structure in the infrared than we've seen from the Earth in these aurora, and we've even flown through the EO flux tube. That's the million amp currents that flow between the moon and the planet and produce the aurora. Survived, yeah, it was a really strong signature. This is a picture that's about to come out in Science any day now, showing that the EO main spot has a lot of structure behind it, and we're trying to work out, is that structure associated with what's produced at EO, turbulence behind EO, or is it produced in the atmosphere associated with where these electrical currents hit the atmosphere? So this has spawned a lot of activity in trying to understand how this whole system works. We flew through, this is the waves data. Only thing you need to know is that for about 20 seconds we had a really strong burst of electric and magnetic signatures. This is the sort of stuff that we see from the Earth and been observing, but here we actually flew right through where those radio signals are produced. EO actually produces, triggers bursts of radio emission as it goes around Jupiter. When it's on one side of Jupiter, it sends the signal to the Earth, and then it goes around and it sends the signal to the Earth on the other side. So every time EO goes around, we see these bursts every few days of radio emission. And now we flew through the source of that radio emission. And similarly, we see very energetic bursts of electrons that are associated with this current system and the radio emission that comes, that it generates. So that's what we've been doing. We've had 13 flybys. We've just been authorized to keep going until 2021, when we hope to get 32 orbits. We're working out what it's like inside. We've got some sense that this cartoon is now probably wrong. It's much less distinct layers, more fuzzy inside, and that deep core of material is more mixed in with metallic hydrogen. Thank you very much. Some movies that are running, we'll keep them running, but I'm sure there are going to be some questions. We can just keep it running, yeah.
We'll turn on the light.
Yeah, it's
In
on
the
the,
overall energy budget internal to the planet,
yeah,
you're talking about these areas where we've got dissolution of this, there's got
Yeah.
to be chemical release from that
Yeah.
and energy. What is the overall contribution of the energy budget to the energy budget from that as opposed to other things that are?
okay, so 318 times the mass of the Earth. When you form a planet from that kind of mass, there's a huge amount of energy that is stored inside. That energy, gravitational energy, is stored. So you can think of Jupiter being a really big hot potato, keeping its energy, compared with Earth being the pea on your plate that cools off very quickly because of the small size. And so Jupiter has retained all this heat, and most of the heat that's coming from the inside is in fact primordial heat or heat of differentiation. There's not a lot of radioactivity because there aren't radioactive elements. It's not like there's a whole bunch of thorium and uranium and potassium and the things that generate a lot of heat inside the Earth. There's just so little of that stuff.
It's still primordial.
So it's primordial heat, yeah. Yeah, so it's almost, it's a failed star, but a very successful planet. Yeah.
Magnetic is off by, like you said, 10 degrees on Earth and 9.5-ish. That's an awfully coincidental number. Is there some magic about that number?
No, there isn't. And the Earth's magnetic field is varying a lot. And the dipole approximation that means, like using the bar magnet tilted, is a crude approximation because the Earth's magnetic field is more complicated than a simple dipole, and Jupiter's is a lot more complicated than a simple dipole. So it's just an approximation, and the number around 10 degrees is a coincidence because the Earth's has changed and has been different, and so, you know, I wouldn't read too much into that one. Remember, Uranus, it's 49 degrees, and Neptune, it's 59 or something. I've forgotten the numbers from Voyager, but, you know, big tilts. Totally different dynamo inside those gas giants. Yeah.
How close is Jupiter in mass to striking up fusion?
I think it's about a factor of 20. I'm looking into it because I think you probably know the answer to that more than I do. I think it's about a factor of 20, too small to have fusion. So that's a lot.
Sure.
Like I said, it's a failed star, but very successful planet. So I don't think it's ever had fusion inside.
Okay.
So, you know, brown dwarf, so considerably bigger than Jupiter.
It's way short then.
Yeah, it's way short.
Good.
Yes. Well, yeah, I agree. Yeah.
Regarding the existence of the JunoCam on the mission.
Yes.
Where were you before it was decided? How did it work? How?
So I was on
who
the,
your-
I mean, I was on the team. I was on the team. There's about 10 of us co-i's, so 12, something like that. And, you know, I've worked from the beginning on this.
Right.
And,
Which side, did you want it or not?
oh, I was quite happy with slapping on a little camera. It's the same as the camera. It's made by men in sciences who make all those cameras that go to that bloody planet Mars. So they just took a Mars one, and actually it's amazing to pick it up because it's made out of Templon, and you pick it up. It's about the size of a standard SLR camera, right? And you go, ugh, this is really heavy. Because they've made it to protect it from the radiation. I mean, you've got to have it out there on the. You can't have it behind inside, right? Because you're going to look at something, and so you can't protect it. So any other way except having local protection from the radiation. You've got to protect that CCD that's collecting the images. So in fact, we have several ways of measuring radiation. We use the CCDs or equivalent detectors on the JunoCam, on the infrared GERM, and on the UV instrument, and on the star cameras. We use all of those instruments as well as a radiation monitoring instrument to measure the radiation. And so we got a really good measurement of the radiation. And it's a little weaker than we thought in some places, but sort of more or less comparable to the expectations. So we probably will have issues later in the mission, but right now everything's going just great. All the instruments are working, the spacecraft's working, crossing my fingers, my toes, my legs, everything. Not that I'm anxious. Lockheed did a great job.
So is that gamma?
No, it's just, NeV electrons. So these are charged particles that are trapped in the magnetic field. Ultimately, there's also sulfur and oxygen ions that come from EO that's been accelerated to very high energies, but it's the electrons that cause the damage. And so that's why we're really worried about protecting the instrument.
That's why you think at orbit 32 things are gonna fail?
That's the current, and so that was the plan originally, was to do 32 orbits. We were going to go into a tighter orbit, a 14-day orbit every 2 weeks. And then there was an question about whether or not we wanted to fire the engines, partly because there's issue with another spacecraft and similar engines, and we were worried about it being a good idea to fire the engines on Juno, so we said, let's stay where we are, not fire those engines. So we stayed.
What happens when it dies? Does it go into?
Okay, so the most important thing is we must not hit Europa, because Juno is probably carrying bugs from Earth. We don't want those bugs to get into the ocean of Europa and cause chaos like rabbits and kudzu, like we've done on the Earth. So we don't want to take those Earth bugs and pollute the most likely place where there's going to be life outside Earth is Europa, not that other pivot.
I'll see.
So we'll send it into Jupiter. We'll burn it up. You know, we'll see how it goes. Orbit by orbit, we'll see how we do. Let's see where we are as we get in 2030 orbit, see how we're doing, if everything's good. Maybe keep going a bit longer. We'll go ask for more money if we need to. And you know, if a spacecraft's producing good data, NASA keeps usually keeping their spacecraft going. But you know, maybe we get to the point where the instruments are dying and the radiation's bad, we just say, okay, out of here, we've had enough. It's the usual sort of way. Yeah.
Is its orbit carried out past any of the moon's orbits?
Yes, it goes way outside the moon's orbits, but it's polar, so we don't go close to those actual orbits.
Okay.
We do have a few observations of the moons, but you can't do everything, and we're just not focusing on those moons. So Europa Clipper will get those great ones.
So,
Yeah.
Fran, you know, with that orbit, so it goes way out. You didn't want to circularize the orbit? Or
No,
that, or-
because that would require firing the engines.
Oh, right,
And we
okay.
were worried about firing the engines when similar engines on another spacecraft failed.
Which one?
I don't know, actually,
Right,
to be honest, it may even have been defense. We don't ask.
Yeah.
Maybe these guys know, I don't know. Do you know about this? Do you know?
I don't.
Nothing you can talk about, okay.
Yeah. Okay.
At what point did you decide not to fire the engines? Like, was it after it already launched, or?
No, it was way after its orbit. We'd gone into orbit insertion, we'd done at least one, or we were about completing one of these big orbits. I think that's about what, we also had an issue when the second flyby, there was a software issue, and we had to, usual story, just had to turn the computer off and turn it back on again, and then it all worked fine, right?
Right.
Turn it off, turn it back on again, and then it was fine. And it's worked perfect ever since. Ever since it's been fine, right? So, I mean, it was a software problem, and now it's working great. But along the way, and I forget, you know, I don't remember whether it was the beginning of the big orbit, or the end of the big orbit, or the second big orbit, but somewhere around there, before, we knew that we'd do at least one, maybe two big orbits before we would fire the engines and go in close. And that somewhere along that, you know, this than I do, made that decision. Yeah. But I was quite happy, actually. I quite like it. It's nice. It means that we get a bit of a break between, I mean, you know, if it had been 14 days, it would have been exhaustion, you know. And also from magnetospheric viewpoint, oh boy, we have the most amazing data out there at 100. First time we've been making measurements of the plasma out there with really good instruments. So I'm really excited by all of that. So a little bit personal pleasure there. Yeah.
So Fran, you know, could you tell us a bit about being a woman within the science community? I mean, I am sure you hold your own, and I know you can fight good against the Mars people. But you know, just maybe you got your degree in England, and then you went to MIT.
Yeah. So I worked on
So-
Voyager, and have you guys seen the movie The Farthest yet? The
The
PBS
Farthest?
program, or The Farthest, which is about the Voyager mission.
Is it?
Go check it out. It is so cool. It's made by this The Farthest. It's on PBS, and it was made by an Irish woman, and it filmed a bunch of us talking about the good old days of Voyager. But and there are quite a lot of women in that film, and that's because the woman who made the movie sort of found the women and pulled them together to make the movie. But as well as a bunch of guys. But if you look at the old pictures of the Voyager mission, all of the instrument leads were guys, and the whole, you know, co-investigate team was all guys, even up to fairly late in the late 80s, early 90s, that sort of era. But if you look at the whole team, there are a lot of women involved in the operations and in the doing the data analysis and so on and so forth. So the whole team, there was a much more balanced distribution. If you look at New Horizons, Mission to Pluto, started working on that with Alan, 1989. We started with not very many on the team, 2 or 3 out of 15, say. But then if you look at the flyby in 2015, we took a picture of all the women on the team, and we were at least a quarter of the whole mission. So 30% maybe. So it's really changed over time, and there's a lot more women involved. And the New Horizons, they were up there as deputy project scientists and so on and so forth. The mission operations manager was a woman, the mom, we call her. You know, so things have changed a lot, and there's a lot more women actively involved. Do you know, there's me and Candy and Heidi and a few others, not quite so many, but it's, yeah, it's a cultural thing. You know, that was sort of the way it was. And, you know, I've been treated with huge amount of respect and had great interactions with, you know, I've not had any issues, but, you know, I'm a pretty strong person, right? You know, and you shouldn't have to be, you know, a pretty strong, outspoken person to start. So, yeah, we could do better.
I want to add that. I think it's not all industry that makes that happen. It's not how women are treated as children at home.
Yeah.
Here's your fry pan and your cook set, not here's your math book and your calculator. So there's a lot we can do at home.
Right. And actually, I read something recently about not encouraging young girls to go out and take risks. It's like the guys, it's fine for them to run about and bruise their knees and make a mess. But the young girls, it's all, you know, oh, don't do that, you'll hurt yourself, right? Or whatever. And then the commercial bullshit that's rammed down people's throats about dressing all fancy and all that. Don't get me started.
I was going to ask where your skirt was.
Yeah, right. God, hang on, one skirts and school uniforms.
Yeah.
Anyway, okay, are we,
yeah, you need
I've got
to
to drop
go.
out the veil.
Yeah, so we gotta, but what we like to do, well, let's talk. And, we want to take a group.
I'm a local here. This is our 41st year in the canyon.
Wow.
Believe that.
Turn them off?
Well, we're getting a reflection.
Okay.
I see a reflection.
And
Especially the side ones that serve no purpose.
I've been taking pictures up here since 1997. I've taken some before, but not doing astrophotography per se. This is my first, actually my first try at it. Turned out to be this shot of Hale Bob. So this is April 1st, 1997, from our deck here in the canyon. And all I could see was the comet and the two tails, the ion tail and the dust tail, and that reddish-orange cloud. So it was a twilight shot. I couldn't see any stars at all. So about an 8-second exposure on 800 speed Fuji film. Went to Mike's camera in Boulder. I go, how do I do this? You know, and they just asked me if I had a manual camera and a cable release and a tripod. So that's what I did. The Andromeda Galaxy even came out right here. An airplane flew through the shot, so I had this red line, so we had to remove that. And I got that made into a card through Ancient Images. Used to be out of Boulder, now it's in Moab, Utah. And they gave me, I think, it was like $400 or something. I got 1,000 cards, and they marketed 1,000. So some of those went to other countries. So people said they saw the card, like in Japan and stuff. You know, I got like a nickel for it or something. You know, but it was fun getting started. Then I realized, well, if I can do that, I can do some other shots. This is from 2003, the full moon in, I believe it was August of 2003, when Mars was closer than it's been in, 60,000 years. I got the Mars image via Gary Emerson's, I believe it was a 10-inch scope on my old Nikon D100. And I thought, well, that was the position that was in at that time. I'll just enlarge it so you can actually see the polar cap there. I think it's, I can't remember if that's north or south because it might be flipped over. But anyway, I couldn't believe that much detail, you know, from the planet. But apparently, towards the end of next month, it's going to be, I mean, it's getting bright now. And apparently it's about as bright as Sirius, or will be at the end of July. So lots of Mars action for next month as far as people taking photographs.
And-
So yes,
Just, Dave, you mentioned Gary Emerson. He was the astronomer who lived up Gap Road, right?
yes, so
Yeah.
Richard's neighbor.
So- Yeah, yeah,
Richard's
who had a telescope.
Yeah, quite the observatory there, yeah. He did some great stuff.
He moved to New Mexico almost
Yeah,
10 years ago.
He's in San
Right.
Francisco now.
San Fran now.
And I actually just looked him up the other day and it said Prescott, Arizona.
He's moved again? Jeez.
So I'm not sure. But yeah, he's no longer here, but he was a great guy and we had a lot of fun doing those shots. But I submitted this image, a friend of mine told me to go ahead and do it to the Denver Museum of Nature and Science, and it's in their digital gallery along with the Hale Bopp shot. So I haven't gone down there to see if it's there, but that's what they told me. This is a shot of the full moon setting at dawn, just before, well actually maybe the sun had just come up if you're further east, along the Indian Peak. So every December, January, I get these opportunities from our deck in Crescent Park here to take these kind of shots.
Is that real color? Did you have?
That's pretty close.
Is that purple?
Yeah, it was like ridiculous, yeah. And then this one, this is the partial solar eclipse, October 23rd of 2014. Our group here was together at the Wonderview Cafe checking it out with the eclipse glasses and everything. And let's go back. Anyway, I was going to say, there we go. You can see quite a few sunspots there. I mean, that was pretty strong collection of them at that time. And that was just some, like a Mylar kind of a filter that I just held up in front of the lens to get that shot. Taking it 300 millimeters and then, cropped so you can see it like that. And this is the fiery crescent of the annular solar eclipse in Albuquerque in 2012. And that's with a little point and shoot Sony with eclipse glasses from McGuckin Hardware. Because I had the Mylar, I think it was Mylar filter for my large DSLR, but it actually worked pretty good, for that. There's the dead center there, the center line. I guess I was within a mile of it, where I was at this golf course across from the, what's it called? Hard Rock Casino and Hotel. And there were people there that wanted to see the eclipse. I was set up at this golf course on their deck by their pro shop. So people were coming over because they couldn't stand in the parking lot at the casino. So I was handing out eclipse glasses and telling them what they're going to see if they looked through the glasses. You couldn't really tell just looking out. This is towards sunset, actually. It was just getting a little bit darker, but nothing compared to looking through the eclipse glasses. And I was sort of stunned too. I'd never experienced this before, how much of a ring of fire it was. So there I am on the deck of the golf course. The people at the bar said, well, since you brought all the customers over, from across the street, they were buying me Coronas, even though we didn't have Corona to shoot, But yeah, that was a fun time. This one, this is the total lunar eclipse in April of 2014, and that was a pretty good one. I took it from my deck, and just looking up at it, it seemed like it was just this hanging orange, or tangerine or something. So I think that was about 3:30 or 4 in the morning on that one. This is the eclipse starting in 2015. I'm at the parking lot of NCAR, and I just thought the colors were really interesting as the eclipse was starting. There were a lot of people there, and we could see clouds coming, and people were already saying, we may have to head down away from the clouds. Excuse me. So I decided I'm just going to stay here because I could tell that there would be a gap at some point, and I was actually able to get that. So a little bit, Richard knows more about this, about the amount of light, but it was a little darker on this eclipse than it was in 2014. And this is another in-car special. I just love shooting the moon there because there's no wires, there's only trees if you want them, you know, to move into position to take shots like that. This is from our deck, Raven watching the moon rise. I mean, I was just looking like, dude.
Photo op.
Yeah, but it really it seemed like he was checking it out. His head was turned that way. And this is I believe this was one of the super moons. You know, I can't remember which one to give us phases, but rising above Denver or towards that way, and I saw this light and I didn't know what it was until zoomed in. Those are turned out to be, had to do some internet research. That was fireworks at Dick's Sporting Goods Park that night. So that kind of, you never know, what's going to happen with that. This is Cathedral Rock in Sedona with a moonrise about 10 years ago. But that's just an amazing place. This is Crescent Moon, and I believe this was, may have been Jupiter on that particular one. Those are kind of fun when you have those pairings. And this is a shot near 93 with the railroad crossing and the moonrise.
Moon crossing?
Yeah, moon crossing. There we go. I like it with the shades. There we go.
So that's a prescription so I can see it all better.
They're just really cool. Yeah.
That's it.
And they are.
You're so bright.
This is a moonrise. I really like the clouds and everything. People say, where did you take that? This is from a Taco Bell parking lot. Parking lot photography in Westminster. Off 120th. But I could see it, the shot kind of coming together, and I was trying to figure out where I could.
What were you doing at Taco Bell?
That's brilliant.
This is actually in the evening. Yeah,
Oh, okay.
yeah, because it's
So you set up a tripod?
no.
Well, like
A lot of anything with the full moon, the full bright moon, those are all handheld. Because it's so bright, And I use the camera that I use tonight for the group picture. I use a 70 to 200 VR lens that has the vibration reduction, so can handheld, can do hand holding pretty well with that. So it's really handy. And I have a 1.7 tele extender that I used some longer telephoto shots. Oops. And this one I call Moon Dance. This was about, 15 years ago from our deck telephoto, like at 300, above the Indian Peaks. So another one of those, January, December time of the year, where I get the opportunity where it lines up that way. And we're so fortunate to have the cloud, it's like, so it's really cool. That's just a shot of the full moon with my 4-inch Meade with my, I think it was a Nikon D100. So it was my first digital SLR. And it may have been, not 2003, like 2005, something like that. And here we go into some smoky shots. This is the sun setting with wildfire smoke. You can see some crepuscular rays above the clouds there. So get pretty shots, but of course, kind of like the smoke tonight from the microwave. This is a smoky crescent.
The last one was the sun or the moon?
That was the sun.
The sun. Did you have some sort of filter on your lens?
No, it was that smoky.
You could shoot straight up into the sun.
Yeah. But pretty amazing colors, with all that refraction. Here, this one was really something. This was last year, excuse me, just after the total solar eclipse, with the sun setting, and those sunspots, two of them, those two big ones, each of them produced X-class flares, some of the biggest flares in years. So I think those were some of the ones that actually disrupted some of the radio communication and some other issues. I don't know if they had I don't think they had a coronal mass ejection, because that would have been right at us, you know. Yeah, really, with that much smoke, because I just kind of looked and I thought, well, I'm actually, you know, looking at the sun, you know, without any protection there, but it was that thick. And so I thought we can get a shot of that. And this one, it's like I have no idea why I did it even. I was up on Trail Ridge Road taking pictures of Long's Peak and some other stuff, and I just kind of like swung around and aimed it at the sun, and that's what I got. I call it angelic light. I did call it cosmic flare, or cosmic lens flare, but it's pretty interesting what all the elements in the telephoto lens can create. And this was a shot of the Milky Way, looking kind of down our driveway. And a little shorter exposure, you know, so it's, you can't see some of what they call the rifts, the dark rifts, through parts of it there. I had some other shots too where I had the neighbor's garage and other lights and other things going on, so.
Is that color in there?
And the color was there. But what I did, I modified it. I knocked down the yellow and up the blue, I think, just to, you know, make it more pleasing to me, basically, you know. So no, that wasn't exactly what it looked like. And of course, with the naked eye, you couldn't see that much. But that's like, I think that was like a 15-second exposure or something like that.
And you used tracking for that too? You were tracking? Or was it just 15 seconds?
Because and that was with a 35 millimeter on my camera, which means it was only 50 millimeter view, so a pretty narrow view. So I knew I couldn't go too long without having star trails.
So just a stationary tripod for 15 seconds and it didn't streak too badly?
No.
So to get shots like that, use what's called the law of 500, where you take 500 divided by the focal length that you're using. So if at 50 millimeters, it would be at most 10 seconds, and then you're always going to get star trails, but they're very minimized at those times. And so if you have a 35 millimeter camera or 18 millimeter camera, then you can get up into the 20-second range.
Right. I might have
for this kind.
Yeah, I was gonna say that shot might have been closer to 10. 10 seconds on that one. So this is a composite sequence of the eclipse last August. That was just so amazing. And I had seen some things online on this Facebook page, the eclipse page, and I'd seen some people doing some different presentations, and I hadn't seen anything like this. I thought, well, I wonder if I can do this, and I started to fool around in Photoshop. I was like, oh man, it was crazy. So I did a couple of YouTube tutorials, and I thought, okay, how do you do this? How do you move these? And turned out there was this grid system that you could do for so many objects. And these are all high-res shots that I composed. So this whole thing would be like I don't know, 300 megs or something, you know. It could be the size of the wall kind of thing. But I ended up having to move them manually. Like, you know, I was playing with the mouse like this for a long time. It got to the point where I couldn't quite keep it aligned, so I used my other hand to hold it, you know. And then I could only get so close, and I brought out my ruler and just put it across the laptop screen, and could measure that way to get a balance. So it's pretty close, you know, with that. But what an amazing experience. I'm still thinking of when I'm taking the shots, and somebody yelled out during it was out of totality, and they said, put your hand on the car, or car nearby. It was so cold. I think it dropped 15 degrees or so during the eclipse in Wyoming, something like that.
How many people saw the total
Right, how many-
eclipse? Oh, man. And how many people saw the partial eclipse?
Well, that too.
That's great. Right.
Well, it never happened just a second before.
Combination. Yeah,
That's
so I'm
great.
excited about
You get double our
2024.
money on that.
Yeah.
Yeah, so just, be less than 6 years? I think it's April 8th of
2024.
2024.
2024. Yeah.
Or unless you've got,
Right, unless you're going to.
unless you're going to Chile in the next
Next year.
2019, 2020.
Right.
Tahiti, south of Tahiti.
I think I'd like to go there.
Yeah.
Right. Barely. People are trying to make reservations for 2024.
We'll see.
I don't recommend that, I mean, because a lot of people have reservations years ahead, like in Casper, and they got them canceled, you know, because big money came in and all those kind of issues, so you never know. But the path, if I remember correctly, the shadow comes across in Mazatlan, Mexico, comes all the way up Mexico, through Texas, and then was it Carbondale, Illinois? Crossroads again, like
Yeah.
dead center. And then swinging on up into New York and into Canada. So with good weather, a lot of people say, oh, we're gonna do this stuff back east. I go, this is April. I mean, it'll be April of 2024. You know, the weather may be more of a challenge.
Voice clear in Buffalo.
Yeah, make those plans now, get those reservations.
Their eyes.
Book Buffalo while you can.
You can see where the snow, look at a muzzle on.
This is my favorite, one of my favorite shots with the diamond ring. And I mean, I realized I was shooting usually using my live view, looking at the LCD screen, and would, you know, occasionally look up, and you know, you're actually supposed to put the filter on about now. But I was watching so getting brighter, so okay, got to get a shot of this, and worked out pretty well.
Where in Guernsey were you?
Pardon?
Where in Guernsey were you?
I was, and you could see a little bit, and then this guy says, well, you know, he kind of pointed to where I should go. And I'm looking ahead like, what are those lumps in front of me? There are people in sleeping bags, you know? Slow down a little bit more here, and then moved over. And the people coming in, they were people from Minnesota, people from all over the place. It was so cool to talk to them. And apparently, you know, the population of Wyoming is around 700,000, but for those few days, it was over 2 million. And of course, it all made sense when you're going home. Or in my case, attempting to go home. It was so slow. I mean, you guys know what it was like. And for some reason, it worked out coming in for the eclipse. I had to hit the rest area at Chugwater, along with 500 other people. And everybody was trying to shield headlights and oncoming traffic so they could catch a few winks before going to wherever they were going to go, you know, for the eclipse. But driving home, I can't remember how long it took just to get to Chugwater. And I thought, well, I'm going to have to get something to eat and I need to get gas, along with the rest of the world. I should have pulled over and photographed the Sinclair station and a A&W combined. It looked like something out of the end of the world. I mean, there were 20 cars for each gas pump, and there was a line out the door from the restaurant, and I called Susie and I go, can you see if there's any place to stay here? You know, we were checking online and stuff, because the traffic's moving like, you know, 2 miles an hour.
Yeah.
It was just crazy. But I got gas first. I thought, okay, you know, I got fuel, got enough to make it home, and got in line and got something to eat and stuff. And I was really tired because I didn't sleep much the night before, or the night before that, because Susan and I went to Ogallala. Initially, we were going to do the eclipse in Nebraska, and I kept checking the weather. And I go, I got to go to Wyoming. This is not working, you know. So we drove all the way back. And I slept for just a little bit, and Susie said, no, I'm staying home, thank you. And I left at like midnight, you know, and I felt like going to the Super Bowl or something, looking in the rearview mirror and seeing all the, you know, thousands of cars behind me and stuff. But the traffic was moving. I mean, I was impressed with all of that. For driving home, I go, this is not going to work. I'm not going to be able to make it. So I actually found probably one of the last rooms in Cheyenne.
Oh, you found it.
And yeah, and I got, there was a, what's it called, a Holiday Inn Express, I think, and the guy at the desk said, well, there's just one room and it's a handicap room, and I go,
Oh, they have
no
a
problem.
handicap.
You know, it was like $250, it's like, it's
Yeah,
fine.
yeah.
You know? You have a deal, you know, so, but I'd do it again in a heartbeat. That was the most amazing experience, you know, to do that. And I left the next morning at like 9:30, the traffic was still slow, and it was moving, but maybe 20 miles an hour, 25 miles an hour. Then it picked up, crossing into Colorado, then it slowed to stop and go at Fort Collins, and stop and go at Loveland. And part of it was construction and rush hour from just people had to go to work too. But, yeah, work, what? So,
See, we were smart, we stayed at Casper overnight and drove home the next day.
yeah.
Yep, I was in the camper.
Yeah, that makes perfect sense. So I have greeting cards made out of some of these shots. I'm still working on coming up with something for this. I think I may do like refrigerator magnets or something, to some other product with that. So.
You gotta tie it to a diagram somehow.
Yes.
Mhm. So we'll figure out something. So any questions about any of the photos or any of this?
Is there more?
I don't think, that was the last one, yes.
Yeah.
Make
it's a
sure,
beauty.
I should go back to that one. Guess that's it.
Yeah,
But I wanna
and-
thank John Williams for helping me put the slideshow together.
They got together a few days ago.
We'll do his thing now, I do believe.
Yeah.
If you guys wanna see it.
Just gotta get the same top.
You can't do
I could do
That's
that.
great. So Dave, you did explain your cards are back
Yes,
on
I have
the.
the cards back
yeah.
there, so
And
when
they're
we're done.
$5 each?
They're $5 each, uh-huh.
And I've probably bought about, 15 of your cards.
Oh,
They're
you
great.
bought more than that.
I even gave ones to our garbage and recycling guy. He loved it. And, I just used them like at the holidays to give them some extra money in the card.
We'll give you a special discount, I think you bought over 20.
Yeah, do I get a discount?
He says
on
thank
it?
you very much.
Yeah.
Yeah, no, I love those cards. They're great.
All right. Thank you.
Yeah, thank you, Dave.
Great job, Dave. Thank you.
So, yeah, John, while you're setting that up, let me do one thing. Let me pass this around for anyone who wants to either walk or ride in the 4th of July parade. You don't have to commit, but if you're interested, and just, if I don't...
I can lead the Cub Scouts.
Yeah, oh, right, you'll be with the Cub Scouts. We might be near the Cub Scouts, but sorry. But yeah, it's really fun, and we can get more vehicles, and, if you don't want to walk. We do have a space.
I know, what time is it? What time?
Let me just go see, it's 9:35.
Okay, I'll be there.
No,
I can't.
okay, and
I think I
I'll go
can.
check, see how.
So, just like Leonard does, I thought it would be interesting to do the astronomy news for the past month. And some of this, we're gonna range from Earth to the edge of the universe. So that's how, there's always a lot of astronomy news that goes on, and it's kind of surprising. So we got smacked with an asteroid last week. Oops, there was a video. Where'd it go? Come on. Oh, come on. Anyway, this, about 7 hours before this asteroid hit Earth, and this thing was only about 3 meters, so not a huge asteroid, thank goodness. But this was on June 4th, last week. We have the Catalina Sky Survey is going on down in Tucson, and an astronomer down there actually noticed this thing about 7 hours before. And he calculated the orbit, knew it was going to impact over southern Africa, and it ended up impacting. This is the fireball. That's one of the scenes I just showed you of it coming in, and it looks like a nuclear explosion goes off, and the thing comes in, and this is a really bright flash. And I wish that video would play, but I'm not going to dwell on it too much since we have the space station pass here. And I promised Barb I would get done in 10 minutes. So the alarm's going off. Anyway, do you remember the Oumuamua asteroid, interstellar asteroid that came through the solar system last year? This was the elongated Rama-like object, well, not Rama, that it was clearly from, it was on a hyperbolic orbit. It came into the solar system and left. Boom, out. Well, it turns out that we have another interstellar immigrant that's been hanging out in plain sight. But it's been here since the beginning, near the beginning of the solar system. This other, I can't remember the name of it, it's another asteroid. It sits out in the orbit of Jupiter, almost right in line with the orbit of Jupiter. And you might ask, well, how do we know it's an interstellar interloper? All the planets in the solar system, all the asteroids, they move in the same direction. So when, Fran talked about it a little bit, when the solar system formed, the sun formed and then little eddies formed, the planets, the rocky planets formed in our solar system, rocky planets formed close to the sun, the gas giants and the icy bodies farther out. This thing moves in what's called retrograde. It moves against all the motion of the rest of the solar system. So obviously it didn't form with the rest of the solar system. So they think that maybe back when the sun formed, there was a lot of other stars nearby. These stars tend to form in groups. And so maybe this thing was left over from that. And so it would be interesting in the future if maybe we send a probe to go check this thing out.
How big is it?
It's only 20 kilometers, something like that. It's not a huge thing, but it's a known asteroid. They just only lately took a look at it. Beyond Pluto, we already heard that New Horizon was reawakened for its encounter with Ultima Thule. There's another news story that Pluto, they've done some simulations. Pluto is what you get when you smash about 1 billion comets together. And this is important because they know how, we think we know how the inner solar system formed the planets like Mercury and Venus and Earth and Mars. But when we get out there, where's the material come from? Well, it just accretes over time. This is a picture of, and my computer died. So
Good.
Oh, it's back. I bumped it. Ooh.
Don't touch that cable.
Well, my computer's about to die as well. Let's see if we make it. This is the heart-shaped area of Pluto. And there you see these dunes. And you might ask, well, how do dunes form on an airless body like Pluto? Well, Pluto has enough atmosphere and the gravity's low enough that methane sand dunes, little methane ice crystals, create these sand dunes instead of silica as it does on Earth. And then there's this argument right now about whether to call the next planet we find Planet 9 or Planet 10, Planet X. I personally think we should just leave it at Planet X. But this argument goes back to Uranus was discovered by Herschel through a telescope, and it didn't move quite right in the Newtonian physics world. And so they speculated there's another body out there beyond that was perturbing the orbit. And in the 1840s, 3 people found within a couple weeks of each other discovered Neptune. And they discovered it first by using math, and they predicted where it should be, and there it was. It turns out that Galileo probably saw it, Herschel probably saw it. So in the 1640s or 16 teens, Galileo probably saw Neptune. He just didn't realize what he had seen, because if he had kept watching it over weeks and weeks, he would have seen it move against the starry background. But he didn't do that. He did mark it in his books, and so did Herschel. But the planets still out there still are perturbed by some object. And so there's the speculation that there's an Earth-sized body out there far beyond the orbit of Pluto. It's probably dark, so finding it is gonna be tough. But again, it'll be found by mathematics before it's probably found by visual sight. So this is kind of an interesting thing to watch for in the next years as we do it. Turns out that Alpha Centauri A and B could be ideal for life, especially Alpha Centauri A. If you remember, Proxima Centauri is the closest star to Earth, but it's a red dwarf and it's highly, it's a very active star, has a lot of flares. Just scorches the plant, any plants that would be around it. Now, we don't know if there are plants around Proxima Centauri, but they did look at the flares around on Alpha Centauri A and B. Alpha Centauri B is a little more active, so maybe life would have a tough time, but Alpha Centauri A looks really good. Now, again, we don't know. It's so bright. The stars are close, and Alpha Centauri B actually look like one star from Earth. It takes they're using Chandra, the Chandra Observatory in space to get the resolution that they need to do these kind of studies. So it's kind of cool. Oh, this was also done by Tom Ayers here at the University of Colorado. So a local thing. So a lot of stories about crunching big numbers. There was a story that Einstein's elevator thought experiment. They proved it again. It's one more piece of evidence that Einstein was not human, he was something else. The Einstein elevator thought experiment is, if you were in an elevator going up in a building and there were no windows and you didn't know you were moving, you would still feel the force of gravity. And he takes it one step farther by, if there was anything else in that elevator, it's moving relative with the elevator. And it would be indistinguishable from gravity that the Earth forms. So if a fly's in the elevator with you, it doesn't smash to the floor, it moves along with you. The people at the National Institute for Standards and Technology have very, very precise atomic clocks, and they've got this number, it's predicted to be 0, and they've got it to like 0.002. Is that my computer dying? I wonder.
We're coming up on space station.
We are. So let's end there. Oh, we're back, but let's end there at space station in just a couple minutes. So more astronomy news next month. You'll have to live with it. I think so. I didn't bring besides the interstellar. Well, I didn't see that.
It's one of the last days I was there.
I wanted to go down there and then have a website. Well, we were going to do stuff. I was going to go down for, I don't know if we went to Tennessee.
No, I mean, they were getting a lot of, those conferences, we were supposed to have 6, but we only had 1. But remember, the simulators, they think they can probably phone these things.
Everyone's attention for a moment. Does anyone want to go over to Les Mellon's observatory? I do. Okay, he wants to know, so I'm taking a census. So we got at least 2 people going over there. Well, I left it inside. I might not